Hello everyone, I hope you all are doing good. Today, this is lecture number 22. In the last class, we had discussed about the nucleation rate versus temperature diagram, which we got from the theories of nucleation. And then we discussed how to get the time temperature transformation diagram from the nucleation rate versus temperature diagram. And we said that in this class today we will be discussing about TTT diagram of some iron carbon alloy. But what I think that before we discuss about TTT diagram of iron carbon alloy, we should learn some more nucleation theories related to solid state transformation. Till now we have been discussing about the nucleation theories which involves liquid to solid transformations. But very often we see that a large number of transformations involves solid to solid state transformations. So today we will be discussing about solid to solid state transformations. So till now we had been discussing nucleation theories related to liquid to solid and state transformation. So we have discussed the different theories like what happens in liquid to solid state transformation. Suppose you have a liquid, there are a large number of atoms, so if your temperature is less than the melting temperature, there will be a lot of thermal agitations and you will get large number of clusters of different sizes, variable sizes. So out of these clusters, so clusters are basically collection of embryos and nuclei. So embryos are those clusters. Out of there is a critical size. R star. We have discussed this thing. So the clusters which have size greater than the critical size are called nuclei, and the clusters which have size smaller than the critical size are called embryos. So what happens if you cool the system below the melting temperature? Some of these clusters will say if the size of this cluster is greater than critical size, now it will grow. If this is also bigger than the critical size, it will also grow. But if it is smaller, it will again dissolve and go back into the liquid state. So similarly, we can consider this also smaller size, so it will go back. If it is bigger, then it will grow. If it is bigger, it will grow like this. So ultimately, if it is smaller, it will dissolve. So ultimately, what we get, we end up getting the solid phase out of this liquid phase. So all the clusters which have got the size greater than the critical size, it will grow. This will happen because of the movement of the atom, in the liquid. So embryos will get dissolved and the nuclei will get bigger in size. The nuclei will become bigger in size. So what we can write? So we can write solidification is a two-step process. One is nucleation and then you have growth. So nucleation is, we have seen, this is called nucleation. So nucleation is nothing but nucleation. Nucleation is formation of and then growth of embryos in order to achieve a size greater than the critical size. So this is what is nucleation. So basically, you will, if you pay attention, you will realize that nucleation is nothing but the growth of embryos, to a size greater than the critical size. This is called nucleation. If we consider that the particle which are being nucleated in spherical shape, having a radius r, then we have discussed that the delta G energy of formation is given by minus 4 by 3 pi r cube delta GB plus 4 pi r square gamma SF. And from this relationship, we have also discussed how to get r star, the critical size, because this equation, if you plot, it varies like this. So it has got a critical size, it has got a critical value of energy of formation, this is delta G, here you have R. So if we plot these things, now if we take derivative of this with respect to R, we get the critical value. And the critical value is 2 gamma SL by delta G V. And delta G star is given as 16 pi by 3 gamma SL Q by delta GV square. And delta GV is given as delta GV, which is the driving force. So you can call it driving force for the free energy change per unit volume of the system. It is given as LV dt by LV delta T by Tm. Tm is the multiplier, delta T is the outer cooling, LV is the latent heat of transformation. So these things we have already discussed. So in brief, what we can say, that during nucleation, due to thermal agitations, now a large number of clusters will be formed. Among those clusters, some of the clusters will have size just close to the critical size or little bit greater than the critical size. Those clusters will be called as nuclei, and those nuclei will grow. So solidification can be considered to be a two-step process where nucleation happens and then the growth completes the solidification. The whole liquid transforms into solid by growth of those nuclei. So, and the nucleation is formation of critical embryos and then the growth of those embryos to a size greater than the critical size. So this is what is in general, these are the steps involved in the process of solidification. Today we will be discussing about solid to solid state transformation. I mean the very basic theories of nucleation related to solid state transformation. So why it is important? If you say, for example, if you say consider a eutectic phase diagram. So this is like we can consider it to be simple eutectic phase diagram. So here everything is liquid. So in this axis you have temperature. In this axis you have percentage of beta. This is pure B. Here you have pure. So this is composition. Composition, and here you have temperature. So if you see above certain temperature everything is liquid. Here if you consider a alpha phase, here if you consider a beta phase, here you will have alpha plus beta, here you will have alpha plus liquid, here you will have beta plus liquid phases. So these are the different phases that you will get a different combination of composition and temperature. Of course, in this kind of phase diagrams, we have already discussed how to get this phase diagram from free energy curve. So there the temperature and composition are considered to be the independent variable, but pressure remains almost considered to be constant because pressure has got negligible effect on condensed phases. So today we will discuss about solid to solid state transformation, and we will discuss about the nucleation theories. We cannot discuss everything about the solid to solid state transformation, all the theories of nucleation, growth and everything, but we will discuss the very basic things so that you get some idea about how this solid to solid state transformation differs from the liquid to solid state transformation. What are the different things or the physics that we need to consider in solid to solid state transformation? So if you see this phase diagram, suppose you have a material of this phase only, say alpha phase. You have a material where you have only alpha phase. So you will have a large number of grays, alpha grays. So these all are alpha grays. Alpha. So now what happens? If you cool it, so this is equilibrium phase diagram. So this temperature is called, say, for this composition, this temperature is the equilibrium transformation temperature. So the moment you come down to this point, or if your temperature is below this TE, equilibrium temperature, beta phase will nucleate. So beta phase can nucleate inside this alpha, or it can nucleate on the grain boundaries. Say grain boundaries can be the junction of this multiple grain boundaries, or say junction of two grain boundaries. There can be, or beta phase can nucleate at any end effects, say dislocations, any other defects, twinning, stacking fault. There are so many nucleation sites. So it can nucleate at any places, but the most favorable site is generally the grain boundaries, because those are the high energy sites. So suppose you have if your beta phase is nucleating inside the alpha material, inside which is free from any defects. This alpha phase is free from any defects. This is a single grain. We are considering the beta is nucleating inside the alpha. Then we can consider it to be a homogeneous nucleation. Homogeneous nucleation. But if the beta phase is nucleating so these are the different alpha grains. So if the beta phase is nucleating along the grain boundaries, so you have a nucleation site. So definitely here, as we have discussed earlier, the requirement of energy for the formation of beta phase will be less. So that we can consider to be here also it can nucleate. We can consider this kind of nucleation, as heterogeneous nucleation. So what happens? You see, if a solid phase nucleates inside a liquid, if a solid phase, say similar beta phase, if it nucleates inside a liquid alpha, we are assuming what will happen the moment the beta phase is nucleated. Because of the change in phase, there will be some free energy change. Because of the creation of the surface, there will be some addition of the surface free energy into the system. But the volume of this beta phase and the liquid or the densities may not be similar. So there should be a strain field around the beta phase which should exist. But as the surrounding material is liquid is free to move. Liquid has got the property of fluid, so it will not be able to resist stress applied by the due to the variation in the volume or the densities of the two phases. You remember that when we derived all these nucleation theories, like for homogeneous and heterogeneous nucleation, delta G equal to minus 4 by 3 pi r cube delta G V plus 4 pi r square gamma SL. This we derived by considering a spherical nucleus of radius r. This is the surface energy per unit area. This is the driving force per unit volume, and this is the volume. When we derive this thing, we have made some consideration that the volume or the density of the two phases remain same, but which is not the true. So what happens if the density is not same in the liquid? If the density is not same, their volume will be different. So there will be some expansion or contraction. Because of such expansion or contraction, this will apply some strain to the liquid, but liquid is free to move. So there will be no strain actually. There will be no resistance. So there will be no development of stress. But if you consider a solid, now the moment a solid phase is nucleated, the solid phase beta can have a crystal structure which is little bit bigger than the parent crystal structure. So we can consider a shape like this. So what is happening? We can consider a shape like this. So here the crystal so because of the variation in lattice parameter, the density, because alpha and beta are two different phases, so their lattice parameter will be different. Their density, densities will be different. As a result, their volume will be different. So because of difference in volume, they will apply pressure over one another. So because of this, some strain will be developed around the solid beta phase. So this will lead to the volume change will cause the development of elastic strain energy. So this elastic strain energy will be proportional to the This will be proportional to the volume, size of volume or size of the beta or solid phase. So we call it beta phase here. So now this kind of strain energy, this is an additional term into the solidification. This into this energy terms. So what will happen? This elastic strain energy will also will not allow the solidification or the nucleation to occur very easily. So this is a kind of resistance. So when you have solid to solid state nucleation, because of in summary what we can say, so when you have solid to solid phase transformation, because the density changes, this is because of the change in crystal lattice parameter. There will be the development of elastic strain energy, which is proportional to the volume of the phase being nucleated. So this elastic strain energy will provide some additional resistance to the nucleation. So for solid to solid state transformation, we have to add one additional term into the free energy, into the free energy formation equation. So this will be proportional to the volume, which is 4 by 3 pi r cube. Of course, we are considering a sphere of beta phase of R phase. So this is what we are considering, and we are considering to solid state nucleation. So this is the volume, and then you will have, so we call it delta G E. So delta G E is nothing but elastic strain energy per unit volume. So I hope you have understood what I explained here. Now, you see, if you plot this free energy delta G versus R diagram, before plotting, let us write this delta G as if we take minus 4 by 3 pi R cube, we can write delta GB minus delta G E epsilon Z plus 4 by 3 pi R square gamma epsilon. So this is a volumetric term. It will, this is square term, it will vary like this, like what we discussed earlier. But suppose suppose this variation is only the minus 4 by 3 pi R cube delta GB. Now you have one. So delta GB will be moving because you are subtracting this part, it will become more positive this term. Of course, we are plotting in negative axis, but we have already given this, we have already considered this negative sign. So we can consider the value will be less. So it will move up like this. So as a result, what will happen? If this was the delta G, overall delta G variation, this is 4 pi R square gamma etc. So if this is the total energy of formation considering only these two terms. But now if you consider the presence of this term, what will happen? This will move this little bit up. So this is say we call it dash. This is actually the delta G. So this will be the actually delta G. So what happens? Not only that, and this is initial R star. This is delta G star. Because of this presence of this term, this R star goes to the right. That means R star also increases and delta G star also increases. Because this provides additional value. This is a positive term. So this is or we can simply consider it to be another term. So this will actually we can consider it to the top part also, but for the simplicity we have plotted it like this, both together. So this is summation of minus 4 by 3 pi r cube delta G V minus delta G E. This dot. This dot is the one in absence of this delta G term. This is the one in absence of this delta G term. So this is this equation. So what happens? Elastic strain energy. If you see delta GE, it increases R star, also delta G star. So because of the presence of this strain energy, now the critical size increases as well as the critical energy of formation also increases. So the barrier increases. That means that now the formation of the nuclei will be much more difficult, because the nuclei you need to form bigger nuclei as well as you need to supply more amount of energy, or you need to overcome the higher activation barrier, which is delta G star. Now, if you want to find out the critical size and the critical free energy, similarly, like what we did earlier, we can take derivative and then equate it to 0, it will give me R star. So when we get the R star will be nothing but similar to, here we don't write SL because this is alpha and beta. So we write gamma, alpha and beta. So you should correct it. We call it gamma, alpha, beta. So this is the interfacial energy between the alpha and beta phase. And then you have delta G V minus delta G E epsilon. So this is, you should understand that we have already considered that this energy is positive. We have already considered the sign. We have considered that there will be negative change in free energy, there will be positive change in surface free energy, there will be positive change in strain energy. So you should remember these things. So we are not considering the sign, we are just considering the values here. So this will be the critical radius. Similarly, if you put this value in this equation, then you will get delta G star. The equations are very similar to homogeneous nucleation, that involves liquid to solid transformation. Only the difference is you have this negative term here. Now, of course, when you consider the absolute value, then you have 16 by 3 pi gamma alpha beta cube by delta G minus delta G epsilon square. So you should check this equation this also you should check, but I believe these are right. So these also explains, you see, if delta GE increases, this term denominator will become less. So if it becomes less, R star will increase. So you see, this is what more surface energy, the presence of surface energy term here will increase the critical size. The similar thing will happen with delta G star also. The presence of this energy term, moves this curve up, the overall behavior also goes up. So the critical energy also increases. So this is how the elastic strain energy, affects the nucleation. Now, note one thing, as I said, at T less than equilibrium temperature or the transformation temperature, we have already considered delta GV will be negative, gamma alpha beta will be positive, and then greater than 0, delta G epsilon will be greater than 0. So you should use only the absolute values here, irrespective of the sign, what you get. So now let us study a little bit about this. Suppose if you see this equation, R star is 2 gamma alpha beta divided by delta GV minus delta G epsilon. So these are absolute values, as I said. So what will happen if delta GV is less than delta GE? This term will become then delta G V minus delta G epsilon will become negative, less than 0. So if it is less than 0, what will you get? R star will be less than 0 or negative actually. So R star negative, this implies that this is not possible. Meaningfully, it is not possible to form nuclei. So, but is it practically possible to have a situation where, say, delta GV will be less than the delta GE? If you see the equation delta GV is given as LV delta T by Tm. This is how we have defined this delta GV term. We need to consider the sign properly, whether positive or negative. So when you write delta T, which is undercooling, delta T is TE minus T. Transition temperature, equilibrium transition temperature minus the transformation temperature. It will be less than this, so we get a positive. So this thing you need to be careful when you use them in the equation. So now if you see delta GV is proportional to delta T. So if your undercooling is less, delta GV will be less. So for smaller undercooling, if your temperature is almost close to T, but less than T, very close to T, or say it tends to T. So what will happen? Delta T will be less, and you have a probability that delta GV will be less than delta G cap. So that means this condition tells you that you have to have a certain level of, you have to provide a certain amount of undercooling, then only nucleation will happen. Otherwise, what will happen if your undercooling is very less, you will get negative term, which means nucleation will be it will be smaller than 0. So nucleation is not possible at all. So your undercooling has to be, above certain threshold value. So what is that value? At what temperature the transformation will begin? So this is what we will be looking at now. So the condition is, then for undercooling, for solidification, or say nucleation, to occur, this delta G V minus delta G E term has to be greater than 0, or say greater than or equal to 0. It has to be positive, because if it is negative, then R becomes negative, it is not possible. So it has to be 0. Now what is delta G? So you see, we know that delta G, we know that delta G equal to delta H minus T delta S at concentration, and then at temperature equal to equilibrium temperature, for the which is equivalent to say melting temperature in case of liquid to solid transformation. Here we call equilibrium transformation temperature. What will happen? Delta G will be, delta G is 0. If delta G is 0, delta H is T delta S. Now delta G at any temperature T will be delta H minus T delta S. Let us remove this, it is not necessary. At any temperature, delta G will be, and now if you put delta H in this, here it will be T. So T in delta S minus T delta S, delta S into T E minus T. So this is delta S into delta T. So this is the free energy of change, and this is free energy change is equal to entropy change and the undercooling. Now if you put this in this equation, what do you get? Delta S into delta T minus delta G E greater than or equal to 0. So delta T, which is T E minus T, will be greater than or equal to delta G E by delta S. So delta S, you can consider it like what we have considered delta G V. Delta G V is per unit volume. So here also you have to consider per unit volume, per unit. So this is another term, you can say molar entropy change per unit molar volume. So mole number into molar volume will give you the total volume. So this is equivalent of saying entropy change per unit volume. So then you see, you get, if you take T this side, T will be less than equal to, T will be less than equal to Te minus delta G E by delta S D. Remember delta S, we have to take the sign only. So you have to take the value only. If you take this, otherwise if you take delta S, V will be less than 0 at T less than T. Delta SD will be S beta minus S alpha by dm. So we are considering the volume, molar volume. So S beta is the, as the transformation is happening from alpha to beta. So this will be, beta will be less than alpha. So actually you will get a negative value. But here in this equation you have to consider positive. So this is the equation. What it tells you, this is the undercooling, that this is the undercooling that you need to provide in order to start the nucleation. So which is proportional to delta G by delta S B. Now, so from undercooling you can get the T alpha to beta. So transformation temperature. This is transformation temperature. This is equivalent. So actually, this equation clearly tells you that why we need to provide undercooling for this nucleation in presence of this free energy term. I mean, you need to provide more undercooling in presence of this strain energy barrier, elastic strain energy barrier. Now suppose if you see the phase diagram, this part you have alpha plus beta. So we were cooling the system, but now if you heat the beta phase or alpha plus beta phase, the beta will go back to alpha. So there will be reverse transformation. But reverse transformation also, if you just reach this temperature, which is equilibrium temperature, the nucleation of beta to alpha phase may not, beta to alpha phase may not start. You need to provide some superheating. Like here we give some undercooling, here you need to give some superheating. So superheating means you need to apply some superheating. Superheating means your temperature beta to alpha for transformation will be greater than TE, equilibrium temperature for transformation. And this T beta to alpha minus TE is actually superheating. So the question is, what is this? What will be this? The superheating, that the amount of superheating that you need to supply in order to get this alpha phase back in the alpha plus beta mix. What's the alpha phase back from beta? So now what happened? Whatever the transformation is involved, whether it is liquid to solid, alpha to beta or beta to alpha, one thing we know that the free energy will always decrease. So if we plot the free energy versus temperature diagram, so about this, say equilibrium, so this is equilibrium temperature. Above this temperature, alpha phase is constant, stable. So the alpha phase will have lower free energy and beta phase will have higher free energy. But below this, beta is stable, alpha is low. So alpha will have higher free energy. So for any kind of transformation, free energy will decrease. Not only this driving force, the overall free energy that we wrote in the equation, which is the summation of volume free energy, surface free energy and the elastic strain energy, this overall free energy has to decrease. So for beta to alpha transformation also, we can write this. We can write the same condition, that delta G volumetric minus delta G elastic will be greater than or equal to 0. And then here delta G volume will be similar delta S volumetric delta T minus delta G elastic greater than or equal to 0. But here delta T will be T minus T beta 2 alpha, and then it will be greater than delta G E by delta S B. So T will be, sorry, this is, I wrote it wrong. This will be equilibrium temperature, this will be beta 2 alpha. This will be higher than this equilibrium temperature, the transformation temperature, because now we are moving from beta to alpha. Beta to alpha. So temperature of alpha is greater than temperature of beta. So temperature of T beta to alpha minus T E will be delta T. And this is delta S B equilibrium. So you get T beta to alpha greater than or equal to T E plus delta G E by delta S B. Here also it is modulus. So delta S B now will be greater than 0, because delta S B will be S beta to alpha. We are going from beta to alpha, S alpha minus S beta 1 volume. So S alpha will be bigger than S beta, so it will be positive. Now the question is, so you see this is how we can find out the amount of undercooling or the amount of supercooling, amount of undercooling or amount of superheating required to start phase transformation or the nucleation, which involves solid to solid state this transformation. So in summary, we can write alpha to beta, you get T alpha to beta, low temperature will be less than or equal to T E minus delta G E by delta S P modulus. Beta to alpha, we can write T beta to alpha will be greater than or equal to T E plus delta G E by delta S B. So this is then T alpha to beta T E minus T alpha to beta is undercooling, T beta to alpha minus T is superheating. If you see the phase diagram, again we were focusing on this part, alpha to alpha plus beta. This is a particular temperature, a constant temperature at which the transformation takes place. So if you see this diagram, if you see the phase diagram, when alpha to beta or beta to alpha transformation takes place, it occurs at a particular temperature. Now if phase transformation takes place at a constant temperature, during the transformation there will be either addition of heat or dissipation of heat from the system. So and during the transformation the temperature remains constant. This is what we know. Of course this is for a particular composition. If a composition remains constant during phase transformation, so phase transformation is a reversible isothermal process. So that we have already discussed. So now what will happen if we plot the heat flow versus temperature. What kind of behavior you will see? You heat the system, you increase the temperature. So if you increase the temperature, after a certain temperature, beta will transform into alpha at constant temperature, and then again the temperature will increase. This is how you are doing. So this is one temperature T, beta to alpha. Now this is from beta phase you go to alpha phase. If you have alpha phase, if you bring the temperature down after a certain temperature, the same similar amount of heat will be released and it will again come back to beta phase. So this is T, alpha to beta. In between you have the melting temperature or the equilibrium transformation temperature, which is called equilibrium transformation temperature. So this kind of hysteresis loop is formed. In summary, what we can say, during solidification, if it happens from one solid phase to another solid phase, it will be more difficult. You need to go for higher undercooling, you need to go for higher superheating.